So we're continuing the lecture 6. We are trying to see how to solve another frame that is loaded with a UDL. On top of the frame, loaded with a 10 kilonewton per meter, and the pointed load by the side at 4 meters from the support B, 5 kilonewton. To solve this beam, first of all, we have to get the reaction because there are two supports. Unlike when we're dealing with cantilevers where there's only one support, this time there's two supports. So we have to get the reactions. So to start, I want to get reaction A. So I take all the moments about support B is equal to 0 because the type of support there doesn't support moment, doesn't resist moment. So that means the first is reaction A. Reaction A is the first force here. And that reaction A, we have reaction A times 9, that's 9 RA. 9 RA. Trying to any other one turning against it. 9 RA. So because we're talking moment about point B, about spot B. So the other there is a horizontal reaction at point A. There is a horizontal reaction because there's a horizontal force, 5 kilonewton. So there is a horizontal reaction will be developed at point A. Against that 5 kilonewton, there's a horizontal reaction at point A because there's a horizontal force, 5 kilonewtons. Now, but that horizontal reaction at point A will not come into this moment because it is at the same point as point B where we're taking moment. So it's parallel with point B. It's at the same point with point B. If you extend the horizontal reaction at point A, if you extend it, it will meet point B. So it will not develop any distance from point B, any perpendicular distance from point B. That's why its moment will be 0 as far as you're taking moment about point B. So that's why we leave it. Then RA, reaction at A, vertical reaction at A, will develop moment with regard to point B. So that's why we have our 9 RA. Then the load will also act. It will act against point A, against reaction RA, the load. So we have the load, which is 10. That's why minus 10 times 9 squared over 2. That's the 10 as a uniform distributed load. Multiply by 9, give you the total load since it is 10 kilonewton per meter and 9 meters. Then times half of 9. That's why we have this at taking moment at point B. Then the RA turns this way. The load turns against it at point B. Then the pointed load 5 also turn against RA, which minus 5 times the distance from B is 4. This is equal to 0. Total moment at point B is equal to 0. And as such, RA is equal to 47. When we send all this over this way and divide by 9, we get RA to be equal to 47.22 kilonewton. 47.22 kilonewton. If we here now, 9 RA will be all of them this way, changing their signs. Then RA will be all this way divided by 9, and they give 47.22 kilonewtons. That is reaction A. Now to get reaction B, I take total moment about point A is equal to 0. I have the same way. I have 9 RB turning this way. 9 RB about A minus the load. Load turns against it. The load 10 bracket 9 squared over 2 then bracket 9 squared over 2. RB turns the same direction. The load of 10 kilonewton per meter turns against RB with regard to turning about point A. But the load 5 turns the same direction with RB. So plus 5. The perpendicular distance from RA is 4 times 5 times 4. If you extend RA to this point, if you extend the load, the 5 kilonewton load to this point, you see the distance it has from RA, from point A is 4. So that equal to 0. The reactions at A will generate no moment at point A. It will generate no moment at point A because there will be no distance. And that implies that RB is equal to 42.78. From here, RB is equal to 42.78 kilonewton. If I send all this over here and divide by 9, I get RB equal to 42.78. So I've been able to get the two reactions. Then RA, the reaction at A that is horizontal is equal to 5 kilonewton against the horizontal for the system to be in equilibrium. So we've been able to get the reactions in this. We've been able to get the reactions here. So the next thing now is to calculate bending moment. The way we'll be calculating bending moment. We calculate bending moment along the frame. To start with, I start from A. I have M at A. Moment at A is equal to 0. Moment at A is equal to 0 because I'm starting from A. The support at A does not resist bending moment. So M at A is equal to 0. Then M at C is equal to minus, because this is 5 now. This is 5 now. 5 minus 5 times 7. This is minus 35 kilonewton meter. That is the moment at point C. That's the moment at point C. Moment at point C is minus 35 kilonewton meter. The moment in the middle, here, let's say here is let's call it the middle here E. So moment at E will be M at E is equal to the loads that will, when we're trying to get moment at C, reaction A, vertical reaction A will not come in because it's parallel to the distance. That's why it didn't appear here. So now it will come in. So M at the middle here at E is equal to minus 5 times 7, because this 5, the perpendicular distance is the height. Then the vertical reaction is against 5. So plus the vertical reaction, we got the vertical reaction to be ROA to be 47.22 times 4.5. That's the distance at the point E. Then point E is going the same direction with the load. So with the moment we're looking for. So minus 10 bracket 4.5 squared over 2. I've collected the whole forces from A to E have been converted to moment. That is what is exactly on the board there. The whole forces from A to E has been converted. All of them have been converted to to moment. So that gives me 76.24. Is equal to 76.24 kilonewton meter. So the moment at point E is 76.24 kilonewton meter. So now the next thing I will get now is to get the bending moment at that's point D. Bending moment at point D. Bending moment at point D. So if I take bending moment at point D, then I have MR D. MR D is equal to, at this day here, is equal to minus 5 times 7, perpendicular distance to 5, plus this times the whole of this length, that is the perpendicular distance for vertical reaction A, which is 47.22 times 9, instead of the form it was formerly times 4.5 because it is at this middle here. Then minus the load. The load now is 10 bracket 9 squared over 2. And that gave me 0. That gave me 0. 35 times this minus this, that gave me the moment that D is equal to 0. The moment that D is equal to 0, the moment that D is equal to 0. So if I take one moment at any point, even if you call here F, if I take here as F, I can take moment at that point. If I take moment at that point, at that F, if I take moment at that F, I still have here, and at that F is equal to 5. At this point, the perpendicular distance for 5 is 5 times this, that's 3.5 minus 5 times 3.5 minus 5 times 3.5 at this point, then plus 47.22 reaction A, particle reaction A, times this 9 times 9, because we're talking of perpendicular distance, then perpendicular distance, then minus the load 10 times 9 squared over 2. 10 times 9 squared. We're taking moment at this point. 5 won't come in this time around. So that is that. Then I have from this is 4, not 3.5. This was 4, yes. This is the house was 4.5. At this point, when I was trying to get D, I have this times 9, yes. Here it is 4 because the distance is not very at the middle. It was at 4. It was at 4, not at 3.5. It was at 4. That distance of 5 is at 4. That's at 4, not at 3.5. That was the height from here. That is 4. Look at it here. It's not 3.5. I thought the length was at the middle. It was at 4. So then at B, MB is equal to MB is equal to the 5 will not bring in moment now. You have the reaction, the vertical reaction. MB is vertical reaction 47.22 times 9 times 9. Then the load, this will not play, the minus 10 times 9 squared over 2, that's perpendicular distance. Then minus at B, minus 5 times 4, this gives me 0 at point B. The moment at B is equal to 0. So that is the whole moment around all over the frame has been calculated. The moment is force times perpendicular distance. If you maintain that, you get the whole moment around the frame. Maintaining that any distance that is going to multiply any force along the frame must be perpendicular to that force. If it's not, please, it will not give you the moment. So we have just gotten the moment. The next thing to get now is the shear force. The next thing to get is the shear force. Now let's see how we get the shear force. I've gotten the moment. Let's get the shear force all over the frame. The shear force all over the frame. This is 47.22 kilonewton. The RB is equal to RB. We got RB to be 40. RB was got to be 42.78. 42.78. That was our kilonewton RB. So to get the shear force is simple. The first along AC, this 5 will generate the shear force along AC. The reaction, vertical reaction A will not bring for shear force. It's a normal force to AC. So along AC, the shear force is minus 5. The shear force is minus 5 kilonewton along AC up to from A. The shear force at A is equal to minus 5 kilonewton up to C. At C, that is the shear force at this point. So at C, from C now, the shear force at C becomes the reaction. Shear force at C is the reaction, which is 42.78 kilonewton. That's the vertical reaction is the shear force at C. Then as it moves, the shear force gets reduced. At E, the shear force will be the vertical reaction. The shear force at E will be equal to vertical reaction, which is 42.78 minus the load, which is 10 times 4.5. That's at E. At E here, the vertical force minus that at D, the shear force at D. The shear force at D will be 42.78 minus 10 times 9. 10 times 9. So then, and it continues where we continue getting the shear force as we move. So at A, the shear force is minus 5, as I said. At C, it is along this line. It is minus 5 from here to here. So at C, along the Q, at C,